Hello guys, welcome to 6.6. Today we're going to look at 6.6, which is integration by substitution. Now before we get into the details of today's material, let's do a quick review of derivatives. Okay, so let's say I want to take the derivative of a composition of function that is f of g of x. Right? Now, we said this to be with an outer function of f and the inner function of g. Right? We say that f is the outer function and g is the inner function. Right? And to take the derivative of this, we have to apply the chain rule, meaning when we need to take the derivative of the outside function f prime of gx and then multiply by the chain rule, which is g prime of x. Right? So here we can see that f prime, that's the derivative of the outer function, right? And g prime, that is the derivative of the inner function, right? Again, where g of x is the inner function. All right, so what we're going to do in 6.6 integration by substitution is we want to be able to integrate what we have on the right hand side, which is what we got from the chain rule, right? So this is the result of chain rule, right? And we want to go in the other direction to go from here to here by integration. And the technique we're going to use is substitution. Now, a lot of people also call this the U sub, right? Not like a submarine, but stands for U substitution, right? Because U is the common variable that we use to do the substitution. Okay, so let's take a look at how this works. All right, so here is the definition from the textbook. It says that to make a substitution in an integral, we're going to let u represent the inner function, right, or the inside function. So in this case, our inside function will be g of x. Now that can be any function of its form, and we're going to replace that with u. And then when we take the derivative of u, it will be u prime dx, right? So we'll see that in a second. And then, of course, we have a different form of representing u prime, that is du dx. Now, our goal is we want to express the integrand in terms of u. Now, for those of you who are not familiar with the terminology, integrand is the expression or the function that is within a integral, right? So, for example, if I have integral of f of x dx, the integrand will be this term right here, right? So that function will be the integrand. All right, so let's see how this works. Let's take a look at one example together. All right, here we go. So let's consider this example that we have the integral of x cubed times the square root of x to the fourth power plus 5. Now, the inside function that we have is right here, right? That's the inside function, x to the fourth plus 5. All right, so we know that the derivative of x to the fourth plus 5 is equal to 4x cubed. Now you can actually see 4x cubed right here. So that can tell us something about that this x cubed actually came from chain rule. All right, so in this case, it will be a nice approach to perform substitution or U sub. All right, so let's go ahead and perform U sub. All right. I'm going to copy that down here. Okay, and start from scratch. So first things first, we're going to let the inside function be equal to U. right? So on the right hand side, I'm going to write u is equal to x to the fourth plus 5. Right? That's the first step, right? Finding u sub. Finding u sub. All right. Now the second step is we are going to take derivative of whatever u sub is given to us, right? So in this case, we picked u to be the inner function, which is x to the fourth plus 5. Now in most of the case, we are going to pick u to be the inner function. All right. Now let's go ahead and take derivative. Take. All right. So the next step is we're going to take derivative of u. All right. And let's do that. Du dx is equal to 4x to the third power. All right, now what I'm going to do next is I'm actually going to multiply the dx to the right-hand side, right? I'm going to multiply that to the right-hand side. Right? And then we will have du is equal to 4x cubed dx. All right. And now next, we want to figure out what we have in common between the integrand in the original question and what we have right here in du. All right, so we can see that we have the x cube, and we also have the x cube, and we have the dx, right, and the dx here. And whatever we don't have in common with integrand, we're just going to divide to the left-hand side, right? For example, this extra 4 that we have on the right-hand side of the equation, this 4, we're going to divide that to the left-hand side. Okay, that means we have 1 over 4 du is equal to x cubed dx. All right. Now, what we're going to do is the step of substitution, right? So step 3, we're going to do the actual substitution. From the previous step, we know that 1 over 4 du is equal to x cubed dx. Now, notice that we have x cubed and dx here, right? So when we perform the substitution, instead of writing x cubed and dx, we can write them as 1 over 4 du. Right? No more x cubed and x, right? These two can be replaced with this equation, right? 1 over 4 times du. And then we also have the square root of x to the 4th plus 5. So square root. Now, x to the 4th plus 5 is our original substitution, right? So we're going to put that in here, u, okay? And that completes the step of u substitution, right? Notice we started with something that's a little crazy, and after u substitution, we get something that's pretty simple to integrate, right? So let's go ahead and integrate this, all right? That's 1 over 4 u to the power of 1/2 du. Now, that's just a power function, right? So to integrate this, all we need to do is add 1 to the power, right? So u to the power of 3 over 2, and divide by the new power, divide by 3 over 2, which gives us 2/3, right? And then don't forget the plus c. All right, and last but not least, let's just multiply the u in there, 1/4 in there. So that will give us u to the power of 3 over 2 over 6 plus c. Okay. Now, we're not done yet. Here comes our 4th step, which is the reverse substitution. Now, once you have done the integrating step, we want to rewrite u back with our original expression, which is x to the 4th plus 5, right, up here. All right, so we're going to replace this u with x to the 4th plus 5. right? That will look like x to the 4th plus 5 to the power of 3 over 2 all over 6 plus c. Okay, and we're done. Okay. Now, the technique of finding u sub and taking the derivative, the first two steps might take a while to understand, and it might take a while to get used to what we're doing. So definitely take a look at these example if you need to. Otherwise, let's move on to our next example. Before we move on, I forgot to point out one thing. Now, notice that when we pick our u sub and we took the derivative, notice that we found out that we have x cubed in both the integrand and the derivative of u. Now, if they match, then we can use u sub. Now, let me give you another example where they don't match. Okay, so we saw that in the previous example, we can apply substitution when a constant factor is missing from the derivative, right? In this case, it was the 4, right? The 4 was missing from the derivative. Then we can use substitution. However, we may not be able to use substitution if anything other than a constant factor is missing. For example, this integral right here, right? The inner function is x to the 4th plus 5. And when we took the derivative, right, if we pick this to be u, and u prime, or du dx, is 4x to the 3rd power. Now, in this case, notice that we only have x squared in the integrand, but we need an x cube, right? So it's no good because x squared is not a constant multiple of du, or in this case, dw. They're using w now. Substitution works if the integrand contains the derivative of the inside function to within a constant factor. Otherwise saying is that the derivative should be only differ by their coefficients, right? If you can multiply or divide a number to get that exact du dx, right? So in this case, to get from x squared to 4x cubed, you need to multiply by 4x. So which is not going to work for substitution because you have this extra x, right? So cannot use u sub. All right. So let's take a look at another example. All right, here we go. We have integral of e to the power of cosine theta times sine theta. So take a second to think about what is your inner function. Okay. So that will be our first step, right? Finding u sub. All right. What are we going to substitute u with? All right. So in this case, if you guessed it, cosine theta is going to be our inner function, right? Our outer function will be e to the power of something, right? And that something is cosine theta. So cosine theta will be our inner function, right? So here we go. U is equal to cosine theta. All right, so that's our first step. Step 2 is take derivative. I'll notice that in this case, our independent variable is going to be theta, so I want to be a little careful. All right, so du d theta is going to be derivative of cosine is negative sine. Okay, now let's check. Do we have a sign in our integrand? Yes, it's right here. All we're missing is a -1, right? So to get from sine to negative sine, all we need is a factor of -1, which is fine, right? It's a constant multiplier, right? So we can do u sub. Can use u sub. All right, but we're not done yet. Let's multiply the d theta to the right-hand side. Du is equal to negative sine theta d theta. Now, since we didn't have a negative sign in the integrand, we're going to move the negative sign to the left-hand side, right? In the integrand, we have the sine and d theta, which is what we have here. Right? So we're going to move the extra negative sign to the left-hand side. Right? So we have negative du is equal to sine theta d theta. Right? So we can replace all the sine theta d theta with just a negative u, which is very nice. Okay. Step 3, substitution. All right. So we started with e to the power of cosine theta, sine theta, d theta. Right. So e will be there. Cosine is now just u, right? We picked our u to be cosine, the inner function, right? So that's just a u. And all of these, sine theta, d theta, that can be replaced with just a negative du. Like that, okay? And we can keep going, right? Multiply it out. We get integral of negative e to the power of u du. So that negative sign we can actually bring on the outside, okay? Like that. And the integral of e to the u is just itself, right? So it's negative e to the u plus c, okay? And that's it, right? Step 4, reverse substitution. Right, and to do that, you just replace all the u back with the original expression that you had. So it's going to be negative e to the power of u. U is, again, cosine theta from the beginning, right? Cosine theta, and then plus c. And we're done. Okay. Very nice, very straightforward. So let's take a look at this example from the beginning. All right, so we started with the integral e to the cosine theta times sine theta. So the inner function, as we determined, it's going to be in the exponent of e. Right? That's going to be cosine theta, so we set that equal to u. Once you have picked your u substitution, you're going to take derivative of this, and you will get what we have here in step 2. Du d theta is equal to negative sine theta. Right? Multiply the theta to the right-hand side, and then figure out what's common with the right-hand side and the integrand. Right? Usually you will have the d theta and then maybe some extra factor in there. In this case, it's sine theta. So this negative sign is extra, so we move to the left-hand side. We have negative du is equal to sine theta d theta, which this whole thing appeared in our integrand. Right? So we're going to replace sine theta d theta with negative du, which is what we have on the left-hand side here. And then you will get this expression. Okay. And next, just go ahead and integrate it. Once after you're done integrating, you do a reverse sub, replace all the u's in the expression with the original substitution. In this case, it's cosine, right? So your final answer will be negative e to the power of cosine theta plus c. Okay. All right. So the two examples that we saw earlier, they were indefinite integrals, right? We didn't have to evaluate anything. All we need to do was to find the antiderivative. Now, when it comes to definite integrals, there are two methods that you can do, right? So we are going to talk about these two methods, but it's up to you on which method you would like. And I'll show you both. I'll give you their pros and cons, and then you can decide for yourself. The first one is compute the indefinite integral expressing as an antiderivative in the terms of original variable, and then evaluate the result at the original limit, right? So the first method is basically the same thing that we did in the previous example, right? Once we get the antiderivative, and then we evaluate the bounds. So it's the first method is just the same thing. You finish finding the antiderivatives, and then you evaluate the bounds. The second one is convert the original limits to new limits in terms of the new variable, and do not convert the antiderivative back to the original value. So the main difference between these two is that the first method requires a reverse substitution, right? Which was step 4, right? And the second one, we no need for reverse substitution, right? But we do need to play around with the bounds or the limits of integration a little bit. Okay, so we are going to take a look at both of them with the next example. All right, here we go. Let's start with the first method, right? Method 1. So method 1 is same thing as what we've been doing, right? I want to finish all the integrals and then evaluate the bounds, right? So for now, we can actually ignore the bounds and evaluate the indefinite integral dx over 5 minus x. Now, in this case, let's start with step 1, picking our inner function, right? So you only notice that this binomial in the denominator. So let's just pick that as our inner function. Right? So u is equal to 5 minus x, right? And the next du dx is equal to -1, right? Multiply the dx to the right-hand side, we have du is equal to -dx. Right, now notice that we only have dx in the integrand, right? We only have dx, so we're going to move the negative sign to the left-hand side. So we have -du is equal to dx. Okay, let's go ahead and perform our substitution. So here, I can rewrite this integral as -du to replace dx over 5 minus x, that's u, right? All right, and that's pretty simple, straightforward, right? Let's rewrite it a little bit. I'm going to bring out the negative sign and then 1 over u du, right? The integral of 1 over u, or 1 over x, is just ln of that thing, right? So this is equal to negative ln of the absolute value of u plus c. All right, and then do reverse substitution, replace u back with the original expression, which is negative ln of absolute value 5 minus x plus c. Okay. Now, since this is the indefinite integral, we have the plus c here, right? But what we really want to find is we want to evaluate that from 1 to 3, right? So here we go. I'm going to rewrite everything. Integral of 1 to 3 dx over 5 minus x is equal to negative ln of 5 minus x evaluated from 1 to 3. Now notice that I dropped the plus c in here, right? Because we are actually evaluating the definite integral, and as we talked about in the last section, we can drop the c when we are evaluating a definite integral. All right, so let's go ahead and evaluate them. So first we have negative ln of 5 minus 3, right, minus negative ln of 5 minus 1. All right, and let's see what we have. That's negative ln 2 plus ln of 4. Okay. And if we rewrite this a little bit, we get ln of 4 minus ln of 2. And by the quotient rule of logs, we can rewrite this as ln of 4 over 2, which is equal to ln of 2. Okay? And that's our final answer. And that's the first method, right? You evaluate the integral like it's an indefinite integral. Once you get that, replace it back into the original integral and evaluate the bounds, the limits of integration from 1 to 3, right? Okay, so let's look at the second method. Now, the second method is a little different. We are going to keep working in terms of u. Okay, we're not going to do reverse sub. So unlike the first method, we cannot evaluate it like it's an indefinite integral. We have to work with this. but you're going to see it's very, it's not that complicated, hopefully. All right, so first, same thing. We're going to pick our u to be 5 minus x. All right, and same thing with du, right? Du dx is -1 times -1. And then multiply the dx over, we get du is negative dx. And since we didn't have a negative sign in the integrand, we're going to move that negative sign to the left. So negative du is equal to dx. All right, now, usually at this step, the next thing is we are going to go back to substitution. But since we're working in method 2, we have to worry about the bounds. Okay, the bounds 1 to 3, x equal to 1 to x equal to 3. We want to convert to u, right? So when x is equal to 1, we have to figure out what u is when x is equal to 1. So we know that u is equal to 5 minus x. So when x is equal to 1, u is equal to 5 minus 1, which is equal to 4. Right? And same thing with x equal to 3. When x is equal to 3, u is 5 minus x. So u is 5 minus 3, which is equal to 2. Right, so now our integral, instead of going from 1 to 3, it's going to go from 4 to 2. Right? So our new integrals in terms of u completely in terms of u is going to look like this. Integral, now the bounds, instead of going from 1 to 3, is now going from 4 to 2. Right? These are our new bounds. Right? 4 to 2. Right? Keep in mind that you have to keep the same bounds, right? So 1 is now 4, so it's still a lower bound, and the upper bound is 3, and now it's 2. Right? It's okay if you have a lower value in the upper bound. Right? That's fine. Right? It doesn't have to go from 2 to 4. It can go from 4 to 2. All right, and let's go ahead and continue the rest. All right, so dx is now negative du over 5 minus x is now just u. Right? So we're looking at negative integral of from 4 to 2, 1 over u du, like that. All right, and we know that the integral is going to be negative ln of u going from 4 to 2. All right, so let's see what we have. That's negative ln of 2 minus ln of 4, which after we multiply the negative sign in, we get ln of 4 minus ln of 2. I can do the same thing by the quotient rule of log. This is equal to ln of 4 over 2, which simplifies to ln of 2. Right? And they are both the same thing. Right? They give us the same result. Right? So both of these methods are a little different. Right? Pretty different, I would say. Right? One, we're working in terms of x. And the second one, I forgot to write method 2. We are working in terms of u. Now we can work in terms of u because this is a definite integral, and we know how to change our bounds from x's to u's, right? So when you are working in terms of u, not only you have to take care of the integrand, you also have to take care of the limits of integration. Right? Change that to u if you prefer the second method, right? Now let's take a look at another example. And again, I'm going to talk about both methods here. All right, let's start with the first method, method 1. All right, we have integral from 0 to 2 of x times e to the power of x squared dx. All right, so since it's method 1, we can evaluate the indefinite form first, like that. All right. Next, pick the inner function, right? In this case, it's going to be x squared. U is equal to x squared. And then take derivative, du dx is equal to 2x. Multiply the dx over 2x dx. All right, now let's check. In the original integrand, we have x and dx. And here we also have x and dx. The only thing missing in the integrand is just 2, right? So we're going to divide the 2 to the left-hand side, right? So we have 1/2 du is equal to x dx. All right, that's good, right? Because x dx are both found in the integrand. So we can continue our work there, right? So rewrite our indefinite integral as 1/2 du, right? Now the x and the dx are taken care of. Next, we just need to write out e to the power of x squared. Now x squared is now in terms of u. Now one thing you can check when you're doing u sub is that after you do u sub, is there any x left, right? If you do u sub correctly, there shouldn't be any x's left. Everything should be in terms of u. Okay, so that looks good, right? And the integration of 1/2 e to the u, it's very simple. I'm going to put the 1/2 on the outside. Integral of e to the power of u du. And the integration of e to the u is just itself, right? 1/2 e to the u plus c, of course, since it's an indefinite integral. But keep in mind that when we are evaluating definite integral, we can drop the plus c. All right. So we have everything we need. Actually, this is the first method, so we have to do reverse substitution. Right, so e to the power of u is now e to the power of x squared plus c. Okay, now we can go ahead and evaluate the indefinite integral. Okay, let's go here. So that can be written as 1/2 e to the power of x squared and evaluated from 0 to 2. All right, because we have done the integration part already, all we need to do now is evaluate the function at the bounds, evaluate the antiderivative at the bounds, which is 0 to 2. And we can drop the plus c again because it's a definite integral. All right, so let's go ahead and do that. 1/2 e to the power of 2 squared minus 1/2 e to the power of 0 squared. All right, so that's 1/2 e to the power of 4 minus 1/2 e to the power of 0. Now, any number to the power of 0 is 1. Right, so we have 1/2 e to the power of 4 minus 1/2. And we can factor out the 1/2 if we want to. It becomes 1/2 times parentheses e to the power of 4 minus 1. Okay, and we're done. Okay, that's the first method. So let's take a look at the second method. All right, the second method is now going to be in terms of u, right? So we're just going to work with the integral here, right? And again, let's start with the u sub, right? U is x squared, du dx is 2x, and then du is 2x dx, right? So very similar to method 1 as of now. Divide the 2 over, right? So 1/2 du is x dx, right? That takes care of the x dx in here. All right, now next, since it's method 2, we have to take care of the bounds, right? Bounds. X goes from 0 to 2, right? So let's see. U is equal to x squared, right? So u is equal to 0 squared. That means u is 0. And for x equal to 2, u is equal to x squared. That means u is 2 squared, which is u equal to 4, right? So now the new bound is to go from 0 to 4 in terms of u. Okay. Oops. Right, that's the new bounds. All right, and let's take a look how that works. All right, so the integral is now going to be from 0 to 4, right? Because we're working in terms of u. X dx, is now 1/2 du, right? 1/2 du. And then e to the power of x squared, right? So e to the power of x squared is now u, so e to the power of u. Right, so now everything, this whole integral here is now in terms of u. Even the bounds. Okay, so let's continue. 1/2. So I'm bringing out the 1/2 e to the u du. Right? And to integrate e to the u, it's itself, right? It's the same thing, e to the u. Now evaluate this from 0 to 4. Okay? So I have 1/2 times e to the 4th minus e to the 0, and we know e to the 0 is 1, so that's just 1/2 e to the 4th minus 1. Okay, and we get the same thing from our previous example. Okay, so again, both methods work. It's just your personal preference on which one you like, right? Do you like method 1, working as an indefinite integral and then evaluate the bounds at the end? Or would you like this method 2, where you can just work in terms of u and you don't have to worry about anything about going back to x? And one thing with method 2 you want to be careful is you always want to take care of the bounds, right? The bounds has to be in terms of u as well. Okay, so both methods are very fun, very nice to work with, and just pick one that you like. All right, and that'll be all for 6.6 integration by substitution. And thank you guys very much. I'll see you next time.